Okay, let's go back to these two terms, variance of B0 hat and variance of B1 hat. And then in the previous video, I remind you that for this n to the power of -1, you can actually put the n in the denominator here. And then this total sum of square of x is in connection with x but not y, as in the R² calculation. So this is the equation. So the total sum of square of x is all about the dispersion of the x around the sample mean of x. And then ideally we want the variance of B0 hat and variance of B1 hat to be as small as possible. Okay, and then the first factor is the sample size, and okay, I think it only has an impact here. Okay, because n only features here. So remember, as I said before, n to the power of -1 is actually means 1 over n. So you can put the n here. So as sample size increases, then the denominator increases, and then the variance of B0 hat would decrease, because ideally we want to collect information from as big a sample size as possible, which approaches population size. Secondly, we actually want greater dispersion of x around the mean of x. In other words, we want the total sum of square of x to be larger. Then it means the denominator term gets larger. Okay, and then it would mean variance of B0 hat and variance of B1 hat would decrease. Okay, and this is the explanation. By the way, you will see the more official explanation from this paragraph. I just do some screen capture from chapter 2, but here's the more simplified explanation. If the variance of x increases, both the variance of B0 hat and variance of B1 hat would decrease. Then it is good news. The explanation is the more spread out is the sample of the x, or the explanatory variable, the easier it is to trace out the relationship between x and y, or expected value of y. That is, it is much easier to estimate B1 and subsequently B0. In other words, I would prefer the sample collected has a wider range of x, let's say from 1 to 15 instead of the narrower range 1 to 3. So graphically it looks as follows. I prefer this wider range of x. Okay, then I can more precisely estimate the relationship between x and y. But if I only collect but if x has such a narrow range, as in the second graphical sketch, only from 1 to 3, then it is hard to precisely estimate the relationship, especially the slope. Okay, here. Do you really think the slope is that steep? Okay. Okay, so I think we can more accurately estimate the slope parameter if we have a wider range of x. And then if we can estimate B1 hat more precisely, then it means B0 hat would also be estimated more precisely. And then, of course, this is the important message. As the variation of x increases, meaning the total sum of square of x increases, then both variance of B0 hat and the variance of B1 hat would drop. And then finally, this is the bad news. If the variance of the error terms increases, then it means I commit like underfitting and so forth. Okay, then both the variance of B0 hat and variance of B1 hat would increase, then bad news. So it means if this term increases, or the numerator increases, then sorry, both variance of B0 hat and variance of B1 hat would increase. Okay, the more variation in the unobservable affecting y, or the more noise there is in the U, or the disturbance terms, then the greater the variance of the error terms, then making it more difficult to precisely estimate B1 hat and subsequently B0 hat. Okay, then I think that's it for this chapter, simple linear regression or bivariate regression. Then the next chapter is about multivariate regression.